Okay, this actually is a nice image to follow on to the last talk. This is a image that was posted on the Lunar Picture of the Day in early July, obviously obtained by an amateur astronomer. It's of a lunar eclipse, and he's done a beautiful job of arranging this sequence of the moon going into eclipse, in particular arranging it so that the shadow of the Earth can be seen, and the relative size of the shadow of the Earth as the moon slips into it. I did doctor it a little bit. I flipped it and put the moon down at the bottom so it really underlines the mysteries and questions we have about the moon. But nevertheless, I think it's a beautiful picture and helps us to remind why we're all here to understand the mysteries of the moon. And I'll be talking about issues that come from the moon mineralogy mapper. Very briefly, I'll go through a very short form of background, some of the good news, some of the bad news. And then I'll only have time to just very briefly do a short statement or summary or a reminder of some of the highlights that have come out of the data over the last year and a half, and end with a short statement of things that have yet to be done and we certainly would hope to see done in the future. First of all, background. The good news is that the instrument was successfully launched on the Chandrayaan mission. This was, as you know, a first for the Indian Space Agency, and it was a marvelous success, very successful launch. Second good news is that over the course of the 10 months that the spacecraft operated, we were able to piece together global coverage. And piece together, I show you the three principal sequences of data taken at different periods in the mission. And when you put those all together, it covers approximately 95 to 98% of the surface. So that's good news. The second really good news is that the instrument performed marvelously. It is an imaging spectrometer, as you know, and to do imaging spectroscopy, you have to have everything precisely aligned in the optics so that you have good, what's called uniformity across the entire data cube, so that you can, for any pixel on the surface, pull out a full spectrum and use your analyses to understand the mineralogy from that spectrum. And it's worked beautifully. Everything is turned out to be just the way it was designed to be, and we have lovely spectra to work with. So that's the good news. The bad news is, of course, that there were problems encountered on the way and in orbit. In particular, the spacecraft had very challenging thermal environments that was highly variable. Halfway through the period in orbit, the engineers decided to change the altitude to move it from a 100-kilometer orbit to a 200-kilometer orbit, which was more benign, and hopefully the spacecraft would be able to last a little longer. The impact on that is that they weren't able to acquire as much data as they would like because it was very difficult in the thermal environment the spacecraft encountered. For our data, and this is sort of summarized over there on the right, if you follow the red line, that's the temperature that our detector encountered over the course of the mission. And the blue line is the geometry on the surface, something called beta angle, which you can roughly say is the phase angle at the equator. And you can see there were periods where our detector was nice and cool, which was what you want. But unfortunately, those were periods when the sun was very low, so we had very low lighting. For the periods where the sun was nice and high and just the way you want it for spectroscopy, unfortunately, the temperatures were very hot. So we have this conundrum, which was not, we had an extreme environment to deal with, and that obviously had impacts on our data. There's a poster that Noah Pieters providing. You can go and talk to him and any of the other MQ people around if you want to hear more about how we've dealt with some of these issues. So let's move on. The status of the data is that we've delivered all the raw data to PDS. We've delivered one calibration version, what we're calling R4. Yes, we started with A. When we got to R4, we delivered it to PDS. We have delivered, we have created the level 2 data, which is the reflectance data based on the R4 data. We have delivered that to a repository at Brown, but we know we can do better. So we are in the process of recalibrating the data now that we have the data coordinated and have been able to identify the issues between these different major periods of observations. And we'll be recalibrating the entire data set for level 1B, redelivering it in September. We expect this to be calibration version Y. And in coordination with that, we'll be delivering a full reflectance level 2 data as well. We will be holding an additional MCube tutorial at the DPS meeting this fall, and we'll make available the charts that go along with that for those of you who've been following and working with MCube data, keep you up to date on how things have progressed. Okay, let's move forward. Let's go to some of the highlights rather quickly, and I'll hope to leave you with some of the good things which is why we're doing this. Early on, you may remember, when we first got to the moon, we had a lovely sequence of data that went right through the Oriental Basin. One thing we found was that when we looked at the Inner Rook Mountains, we found a composition which we had not seen with telescopic data, namely that we were able to identify massive and pure plagioclase by identifying the crystalline plagioclase band at 1.25 microns, in addition to what we're calling the shocked version. And the entire Inner Rook Mountain is composed of essentially anorthosite, which really gives a very strong support to the products of the magma ocean description of lunar evolution. There's a poster concerning lunar plagioclases that will be up tonight, and actually comparing MCube data with diviner data. I encourage you to go see that as well. Moving on. Of course, I'm sure you all know about the discovery of the superficial water on the moon early on in the mission, based on the detection of OH and H2O in the 3 micron areas shown up in the upper left there. What you have to do is remove the thermal component, that one plot that has a thermal component shown in red. One of the masters on our team who has been able to estimate the thermal component and remove it has produced these updated plots you see on the right, one for an estimated distribution of OH and one for an estimated distribution of the water. The main message is that it's pervasive. There's no question about OH and H2O being pervasive across the surface. You do have to deal with thermal contribution issues, and there's quite a bit of diversity. Clearly, the Mare Highlands have quite a bit of diversity, and that's an important issue that we're still trying to understand. Clearly, what's needed is more regional and quantitative assessment, and most importantly, and unfortunately we don't have this, you need temporal variations in order to understand the origin of this material and the physics behind its creation and movement. Going on to the mineralogy, shown on the left is the wavelength range of M-cube with the typical lunar minerals. I've already talked about the plagioclase there, shown in blue. The sequence of minerals that we normally talk about are the olivines, the pyroxenes, the more mafic minerals. These have highly diagnostic absorptions, and as has been mentioned several times today, these features typically weaken in the space environment by a combined process known as space weathering. The features become weaker. A mineral we hadn't talked about because it was just a trace element and had not been seen spectroscopically before is the mineral spinel. Well, it turns out that this turns out to be very important, and there's 2 forms that I'm showing over on the right. The purple one is the magnesium form of spinel. It's a magnesium spinel, has very strong absorption at 2 micron and virtually nothing happening at 1 micron. And the chromite, the more common form of spinel, again has the 2 micron band. This is due to ferrous iron in the tetrahedral site. But at the shorter wavelengths, it has a lot more features. So the magnesium spinel and the chromite or chromium-rich spinel are readily identified spectroscopically. Well, you may know that one of our additional surprises is, quickly, at the far side of the moon, we found a area that has no mafic minerals, but has abundant magnesium spinel. This is the purple area shown here. The whole area is typically feldspathic, but there's a few areas along the ring of Moscoviense that has this unusual new rock type. It's a magnesium spinel rock type. In addition to that, we also see areas of very olivine-rich and very orthopyroxene-rich. All of these three types of materials have no crater associated with them. They're well-developed soils. The only way you can identify them is spectroscopically. It's a beautiful area to look into the lower crust of the moon. And that has been published in 2011. This year. Move on. We need experimental constraints from the petrologists to understand how these lithologies can be formed and the depths and how the crust evolution is constrained by these new results. We found a second exposure of this, which has even a stronger spinel band there on the right, in the crater Theophilus. This has recently been published in GRL, and one of the nice things about this crater, of course, is it's on the near side. It's a wonderful, accessible area to get this new rock type with a sample return. Moving on, the other form of spinel also has been identified on the moon. This was reported earlier by Jessica Sunshine at LPSC. It's in a surprising place. You may recognize those three areas of dark mantled material in the upper left, Rima Bode and Sinus Astium. Rima Bode, it turns out, isn't very interesting, but the ones further south is chock full of the chrome spinel. These are the only two locations of pyroclastic deposits that clearly have brought material from the mantle. These are the rapid ascent pyroclastic deposits and contain abundant chrome spinel in their deposits. And again, this is an excellent landing site, and I'm going to have to move this forward. Smooth, easy to get to. Okay, let's go there. Last, lunar swirls, as always, been mentioned by Ian. They're unusually dry. Every one that we've looked at is dry, really unusual. And last is the young titanium-rich basalts on the western near side are very, very olivine-rich. No question about it. This is an example of one of the few data sets we have of our high-resolution targeted mode data. Move. Okay, well, can I just put the last slide up, back up, the one before this? Okay, this is the unfinished, lots of unfinished business. I'll leave this thought with you. We certainly have more questions that have been raised than have been answered. The water, we need to have the temporal variations. The crust, we need the more complete measurements and higher resolution. And shown down below is the details. You can examine some of the impact process. This is a paper by Jack Mustard at JGR that shows the distinction between olivine-rich areas, impact melt areas, and the relationship between these two are beautifully laid out in these data. And with that, I'm going to be pulled off the stage.
When you say the lunar swirls are very dry, I'm wondering if you see that in your spatial structure. Do you see the swirls in your data?
Yes, definitely, and it's the high albedo portion of the swirls that are dry, not the dark lanes. And it actually helps to identify the swirls in the highlands because you don't have the dark mare to look at there.
Paul Warren, UCLA. Carle, I'm most intrigued by the chrome spinel discovery, and that's really enigmatic. I know it's hard, but what do you infer about the proportion of chrome spinel in relation to other crystalline phases in these deposits?
This one's harder because it's more complex at 1 micron. It doesn't have a lot of other mafic minerals, for example, the olivine that you would expect, say, from some of the other glasses. So right now, it's the chrome spinel, which is the dominant signature that we see in these pyroclastic materials.
But I gather from what you're saying is that it doesn't necessarily have to be tens of % of chrome spinel if it's just glass, if the rest of it's glass.
That's right.
Okay.
It could be glass, but it can't have a lot of other mafic minerals. It's still very dark, so it has an opaque component. And whether that's the chromite or other.
Okay, so it's not totally pathological. Thank you.